Hello everyone, my name is Igor Kunjavskij and today I will guide you through the project I worked on this summer at the Irish Centre for High-End Computing, which dealt with the problem of deploying deep neural networks on the edge in an efficient manner. Now for this project I used the Intel Movidius Neural Compute Stick, which is a small accelerator in USB format. This stick is meant to be used in combination with lightweight computers such as the Raspberry Pi to speed up computations for visual applications. Processing images is in general a very compute-intensive task, even more so if deep neural networks are involved. Lightweight devices that do not provide too much compute power as the Raspberry Pi can quickly become overwhelmed with this task. A solution to this problem would be to just send the data that the device collects to a data center. But often enough, devices such as the Raspberry Pi are found on the edge. Well, edge as an edge of what is reachable by humans with adequate means. This could be a device attached to a satellite in space running Earth observation missions, or underwater robots conducting maintenance on critical structures such as underwater pipelines. Now there's a manifold of possible issues when deploying devices in such regions, one of those being the restricted connectivity. This means sending data back and forth for processing purposes between these devices and a data center is not a viable option. All in all, using an accelerator such as the Neural Compute Stick alleviates a lot of those problems, making it possible for images to be processed on the edge on the device itself. Another problem that remains though, even with the Neural Compute Stick accelerating computations, is that once a model is deployed on an edge device, it's hard to repurpose the device to run a different kind of model. This is where the dynamic part of the title of my project comes into play. The Neural Compute Stick is a highly parallelized piece of hardware, with 12 processing units independently running computations. This way, it is possible to not only have one, but several models loaded into its memory. Even more so, it is possible to switch those models and load new models into memory. This allows to adapt to new situations in the field, like when the feature space changes or the things that are supposed to be detected change. The simplest case of such an occurrence might be the sun setting or bad weather conditions coming up. Another motivation to switch models might also be to save power, as edge devices tend to have limited capacities if it comes to energy sources. Instead of deploying one big model that is supposed to cover all cases that could occur in a production environment, it would be possible to have many small models that could be loaded in and out of memory at runtime. In my project, I investigated the feasibility of doing so and implemented a small prototype that switches models at runtime. This prototype switches between two models detecting human bodies and faces. These models are both so-called single-shot detector mobile nets, networks that are computationally more efficient to be deployed on smaller devices and localize plus classify an object in a single pass through a network, drawing bounding boxes around it. I used OpenCV for this task, which is a library featuring all sorts of algorithms for image processing. Next to OpenCV, I had OpenVINO running as a backend, a toolkit accompanying the Neural Compute Stick, which allows to utilize it in an optimized manner. I eventually tested this model switching prototype by loading and offloading models in and out of memory of the Neural Compute Stick. I did this with a very high frequency of one switch per frame to determine what the latency of such a model switch would be in a worst-case scenario. The switching process includes reading the input and output dimensions of a model by using the XML representation of its architecture and then loading it into the memory of the Neural Compute Stick. On average, this switch caused an extra overhead of about 14% of the overall runtime. To put this into absolute numbers, on average it took my application half a second to capture and generate an output for an image, whereas a model switch in between would add a little less than a tenth of a second to this time. Of course, there's a lot of room for improvement given these numbers. One such improvement would be concerned with the parsing of the model dimensions. I used a simple XML parser to do so and had to read in the input and output dimensions of a model on every switch. Doing this once for all models that potentially will be used on the Neural Compute Stick when the application starts running and saving the dimensions into a lookup table could cut the switch time almost in half. Further speed up of this switch could be achieved by conducting it asynchronously, as while the model is loaded onto the Neural Compute Stick, the next frame can already be captured instead of waiting for the switching process to finish. All in all, I found that although at the current state this prototype would not be applicable to real-time applications yet, given the potential for improvement, it could get there. Yet, if no hard conditions are imposed for it to perform in real time, as is the case for many applications, it is deployable already. So this would sum up my findings on this project. If you would like to learn more about this project, feel free to have a look at my blog on the website of the Praise Summer of HPC 2019. Lastly, I would like to thank my supervisors for their amazing support throughout this whole project, and in general the staff at iCheck for welcoming me and making this stay such a great experience.